This video finishes up Chapter 8 on additions to alkenes. So here again we have the diverse reaction of alkenes. We've looked at how to go from an alkene to a halohydrin, to a 1,2-dihalide, to an alcohol. We learned 3 ways to do that: the acid-catalyzed hydration, the oxymercuration, demercuration, and the hydroboration. We learned how to go from an alkene to a halide using HBr, HCl, or HI. And we also learned how to take an alkene to the alkane using hydrogen gas and a metal catalyst. We're going to finish up by looking at these last 4 reactions. Taking an alkene to a 1,2-diol. It's called 1,2 because the OH groups are on carbons 1 and 2. They're on neighboring carbons. Can we take the alkene to a carbonyl compound? How do we do that? Then can we transform the alkene into a 3-membered ring, a cyclopropane? And finally, can we transform it into something called an epoxide, which is a 3-membered ring containing an oxygen atom? Oxidation is a reaction that involves adding oxygen or losing hydrogens. And this is typically characterized by bond formation between carbon and a more electronegative atom like oxygen. Epoxidation is a type of oxidation. So in this, we start with an alkene such as cycloheptene, and using the appropriate reagent, we end up with the epoxide. So here we have created bonds to the more electronegative oxygen. We've also added oxygen to the molecule, so this is definitely an oxidation. And to do this reaction, we use a peroxy acid, which is a compound that has this type of functional group. That's a peroxy acid functional group. It has a C double bond O connected to an oxygen, connected to another oxygen. So this oxygen here, that's your electrophilic oxygen. And your alkene is going to be your nucleophile. So notice in this transformation that the double bond is breaking, and the oxygen from the peroxy acid is now bonded to both carbons of the original alkene. This is the mechanism for epoxidation. So there are 4 curved arrows, and this all occurs in one step. So the double bond is the nucleophile, and it's going to attack the electrophilic oxygen atom, and at the same time the oxygen-hydrogen bond breaks, and those 2 electrons form a bond with one of the 2 carbons of the alkene. And then the carbonyl double bond grabs this hydrogen, and this oxygen-oxygen single bond breaks to form a double bond between it and the adjacent carbon. And as a result, you get the epoxide and a carboxylic acid as a side product. And the 2 types of peroxy acids that are commonly used would be this peroxyacetic acid and metachloroperoxybenzoic acid, also called MCPBA. The next type of oxidation reaction is a dihydroxylation. So first, notice what's happening. You start with an alkene, and then you end up with 2 OH groups added to the carbons that had been double bonded together originally. So we're breaking the pi bond like we do in all of these reactions, and we're forming 2 new sigma bonds to OH groups. And if we use a particular type of reagent, osmium tetroxide, OSO4, we get syn dihydroxylation. So notice that the OH groups are both pointing up. That is because they added from the same face of the alkene. So remember, alkenes, we talk about having 2 faces, a top face and a bottom face, because we could redraw the alkene. Instead of drawing the line for the double bond, we could show it as an overlap of p orbitals, because that's what it is. So the electrophile could approach from the top or from the bottom of the alkene. And in this case, because of the mechanism, both of the CO bonds are formed simultaneously, so that is why you get the syn stereochemistry. And the cyclic osmate intermediate is shown here. So notice that Those CO bonds are both pointing up. Now, they could also both be pointing down because you will get enantiomers, a mixture of enantiomers. But the point is that they're both going to be up or both going to be down. They're going to be syn. And the first step to form that osmate ester, the mechanism involves 3 arrows. So the alkene is the nucleophile. And here we draw an arrow from one of the pi bonds to one of the carbons of the alkene, then an arrow from the pi bond of the alkene to the oxygen atom, and then we simultaneously break this pi bond and dump those electrons onto the osmium atom. And this is all happening simultaneously, which is why we end up with the CO bonds that are formed being syn to each other. And then in a second step, and the mechanism for this is a bit complicated, so I will not show it to you, but you use a reducing agent, such as sodium sulfite and water, or sodium bisulfite and water. And then that removes the osmium with these 2 oxygens, and you're left with the 2 alcohol functional groups. Osmium tetroxide is extremely toxic, and if you look up the Materials Safety and Data Sheet, the MSDS sheet, you'll see these 3 symbols. It's very toxic, and importantly, there's a risk of serious damage to the eyes. And the reason for that is in the vision cycle, so this would be the rod, you've heard of rods and cones that are in your eye that help you to see. Well, those are composed of rhodopsin molecules, which are involved in this vision cycle where we isomerize 11 trans retinal, shown here, to 11 cis retinal. Well, this retinal, notice it has lots of double bonds. So if your eyes get exposed to osmium tetroxide, they can dihydroxylate those double bonds in those retinal molecules, which will cause blindness. Now, supposedly the blindness will wear off after maybe 6 months, but you definitely want to avoid any exposure to osmium tetroxide if you can. Now, the osmium tetroxide gives the syn dihydroxylation, but what if you wanted anti-dihydroxylation? How would you do that? Well, this involves a 2-step reaction, and the first step is one you've already learned now, the epoxidation. So first you make an epoxide, and then you react that epoxide with water and an acid catalyst. So the way this works is here's your starting epoxide. It gets protonated with acid, so a lone pair on the oxygen is going to grab the H plus from H3O plus, and now we have a really good electrophile, and water is going to attack from the opposite face of the epoxide via an SN2 process, which you're going to learn about in a later chapter. But essentially, we've seen this type of attack before with the halohydrin. The lone pair attacks one of the 2 carbons of the epoxide, and that bond breaks and opens up the epoxide. And then you get to this intermediate, which is followed by one more proton transfer to get to the anti-dihydroxylation product. So the OH is up here and it's down here, so they're anti to one another. And you'll also get the enantiomer because there's going to be no selectivity for one enantiomer or another. Notice the similarities between these 3 key intermediates which we've talked about in this chapter: a protonated epoxide, a bromonium ion, and a mercurinium ion. So the ring strain and the +1 formal charge make these really good electrophiles, and they also yield anti-products because the nucleophile must attack from the side opposite the leaving group. So it can't attack from the same side, from the same face. It must attack from the opposite. And that has to do with sterics, but more importantly, there are orbital considerations that we haven't discussed yet, where there is an antibonding orbital that the nucleophile can only overlap with if it approaches from the opposite face. And we'll talk a little bit more about that when we get to substitution reactions in a later chapter. Another type of oxidation is an oxidative cleavage. So with this, we're going to break the carbon-carbon double bond, and we're going to break it into two fragments. Ozonolysis is one such process. So with this, you're using ozone as a reagent. Yes, the same ozone that you think of in the atmosphere. It's a very reactive molecule that absorbs UV light, which is helpful to humans for reducing exposure to harmful UV radiation. But it can also be exploited by organic chemists to perform a series of reactions. And this is the structure of ozone. It exists as a resonance hybrid of these two contributors. So notice what's happening here. We start with one reactant and we end up with two products. So we are actually cleaving right through that double bond. And at the end of that double bond, we now have an oxygen on each fragment. So the mechanism for this is quite complicated. I'll show you the start of it, but I won't show you the complete mechanism. So to figure out the products for these types of reactions, you always want to just imagine cutting right down the middle of that double bond. And then you now have two products, and then putting an oxygen at the end of each double bond. So the first part of the mechanism involves forming an ozonide. So in this, you have three curved arrows. So this is a lot like the osmium tetroxide mechanism we just saw. So we have an arrow going from the oxygen lone pair to one of the carbons of the alkene, then the pi bond of the alkene attaching to another oxygen atom, and then this bond breaking, dumping those electrons as a lone pair on the center oxygen. And that's called an ozonide. Then the next part of this is a lot more confusing. So now that ozonide is going to collapse and give two fragments. And it does so by having a lone pair come in here to form a double bond, breaking the carbon-carbon single bond to form a double bond with that oxygen, and then breaking this oxygen-oxygen bond to get to these two fragments. But those two fragments recombine to form this ozonide. And then finally, you can use a mild reducing agent, and that's where you get to your final carbonyl-containing products. There are a variety of reducing agents that can be used, but typically you either use dimethyl sulfide, so that's a sulfur with two methyl groups, or zinc with a mild acid such as acetic acid. So here are some examples. So we have this tetrasubstituted alkene. So essentially we think of cutting right down the center of that double bond to get to two fragments and putting an oxygen on either end, which would give us cyclohexanone, this compound, and acetone. Now we could take another compound. So here you find the double bond and you want to chop that double bond right in half. And now you get two fragments and you get two aldehydes. So notice it's important if that carbon has an hydrogen on it, the carbon of the alkene, because if it does, you'll get an aldehyde. If it doesn't, you'll get a ketone. So see how this carbon had two carbons attached? And we got a ketone. Same with this carbon. This is a ketone. But now these carbons had H's attached, and we got aldehydes. There's another reagent that will cleave alkenes, and it's KMNO4 in the presence of acid, potassium permanganate. And this will actually produce carboxylic acids and carbon dioxide if hydrogens are present on the carbon-carbon double bond. So notice here, we're going to cleave right down the center of that double bond, but this carbon of the alkene has a hydrogen, so it's not going to stop at the aldehyde. It's actually going to get oxidized all the way to the carboxylic acid functional group. And then this carbon has two hydrogens, so it ends up being oxidized all the way to carbon dioxide. And this mechanism is again a bit complicated, so it's not presented in sophomore organic chemistry. So with this, you just have to be careful to make sure you know whether or not your alkene carbons had any hydrogens attached so that you can draw the correct products. The final set of reactions are the cyclopropionation reactions. So with these, you start with an alkene, of course, which is your nucleophile, and you're going to react it with an unusual looking thing called a carbene. A carbene is a neutral molecule where you have a lone pair on carbon and two bonds to two other groups. And when you react carbene with an alkene, you get a cyclopropane, so a three-membered ring composed of carbons. Now, one of the most common types of carbenes added would be the dichlorocarbene. And you can actually make this in the lab from chloroform and sodium hydroxide. So here you have chloroform, which has an acidic hydrogen atom. So the base hydroxide grabs that acidic hydrogen and breaks the CH bond. And then you end up with this anion intermediate. But it doesn't hang around very long because the chlorine atom, one of the three, will leave with its electrons to form this dichlorocarbene. And that's very reactive, and that will react with an alkene. So this is an orbital picture of that dichlorocarbene. So the carbon is sp2 hybridized, meaning it has three sp2 orbitals. So two of them are involved in the sigma bonds to the two chlorines, and then the third one is housing the lone pair of electrons, and then there is a vacant p orbital here. And notice how this is analogous to a carbocation, which is sp2 hybridized and has a vacant p orbital, but it's neutral, not charged like a carbocation. And this carbene is a very good electrophile, like the carbocation. So when you add an alkene with chloroform and potassium hydroxide, you get the dichlorocarbene as a product. The mechanism for this is very straightforward. So the carbene is formed as I showed you, and then with two arrows, you have one arrow from the pi bond attaching to the carbon, and then another arrow from the lone pair of that carbene attaching to a carbon of the alkene. And that gives us the product. Now, there's an important stereospecificity to notice here. The alkene, if it's cis or trans, the groups that are cis to each other, for example, in the starting material, will remain cis to each other in the product. If the groups were trans to each other in the starting material, they would be trans to each other in the product. So the relationship of the groups on the starting alkene is maintained in the reaction. Then the final cyclopropanation reaction is the Simmons-Smith reaction. So in this, we're adding CH2 rather than CCl2. So overall, we start with an alkene and we end up with a cyclopropane. But notice the carbon doesn't have two chlorines, it has two H's. The reagents for this are diodomethane, CH2I2, zinc and copper, and you form this carbenoid, which is essentially a source of a CH2 carbene-like structure. One final topic is the formation of polymers from alkenes. A polymer is simply a large molecule consisting of repeating units of simpler molecules called monomers. An example of this would be cellulose, which is just a polymer of repeating glucose units. Alkenes can react with radical catalysts to undergo a radical polymerization, and some alkene polymers are called chain growth polymers. In radical additions to alkenes, you can start with initiation, where you have some molecule like benzoyl peroxide that can be cleaved to give radicals. So this would give a benzyloxy radical, which then further decomposes to form a phenyl radical, a benzene ring with an unpaired electron. Then that will add to an alkene to give this radical. Then that process continues on to generate a polymer until finally you get to the termination where two radicals come together to form a species that's no longer a radical. So depending on what alkene you have, you can get a variety of polymers. So if you start with propylene, you can get polypropylene. If you start with styrene, you can get polystyrene. And here is a table that shows some examples of polymers and their corresponding monomers. So polyethylene is used in packaging and bottles. Polypropylene is used in rope and carpets. Vinyl chloride, PVC, that's used in pipes and insulation. Polystyrene is used in foam. Tetrafluoroethylene, which has the polymer name Teflon, is used in nonstick coatings. Acrylonitrile is used as a polymer in fibers. Methyl methacrylate, which is known as plexiglass, is used in paint, sheets, and moldings. And then vinyl acetate, which when it's a polymer is called polyvinyl acetate, is used in paint, adhesives, and foams. So these have a great variety of commercial uses. So how would you figure out, if I gave you a polymer, what were the monomers that were used to prepare it? So notice the repeating units would be these units I'm highlighting. So your monomer would be those units but with a double bond. So this would be the monomer that was transformed into this polymer. Okay, now it's time to test your understanding. Identify the expected organic product generated from the reaction sequence shown. So first you're going to use osmium tetroxide followed by sodium bisulfate with water. Do you think you'll get 1, 2, 3, or 4? Put your answers in the chat. In this reaction, we're starting with this cyclohexene and we're reacting it with MCPBA, metachloroperoxybenzoic acid. What will the product be? 1, 2, 3, 4, or 5? Now we have another reaction with MCPBA as the first step, but notice we've got a second step, acid and water. What are the products of this? And the hint is that there are going to be 2 products from the options shown. Question 4, what if you use KMNO4, potassium permanganate, and acid? What product would you get here? So as a hint, this is going to be one of those oxidative cleavage reactions. And I didn't show you one with a cyclic alkene, so this is a bit of a stretch to see if you understand the concepts. Now here, you're reacting this alkene with ozone, and it's followed by dimethyl sulfide. What would the expected product be? Here we have another ozonolysis. Instead of dimethyl sulfide, we're using zinc and acid in the second step. And what would the 2 products be as a result? Would it be 1, 2, 3, 4, or 5? Each option shows the two possible products. Now sometimes instead of asking you to give me the product, I might give you the product and ask you to give me the reagents. So if you wanted to take this cyclopentene and convert it to that cyclopropane, what set of reagents would you use? CH2I2 and a zinc copper alloy, MCPBA, chloroform and potassium hydroxide, or osmium tetroxide followed by sodium bisulfate and water. And finally, what if you wanted the dichlorocyclopropane? Which of these 4 reagents would you use?